Morning, guys. Hope you guys are doing well. So, just to finish off, so far in this chapter here, we started off with waves. The whole notion of waves is to transfer energy from one place to the other without any permanent displacement. So, unlike the example of I have a ball and I toss this ball over to my friend, the ball itself actually physically gets displaced. A wave is sort of like this message or this information, the signal that I can send from one place to the other without actually having any permanent motion, permanent displacement. We started looking at the application of waves. Waves do a lot of different interesting phenomena like interference, diffraction, wrapping around corners. We saw it being reflecting and sort of bouncing. And what we did over the last week or so is we started looking at the analogy of optics. So light itself is an electromagnetic wave. As an electromagnetic wave, it's able to transfer through the nothingness of space. It doesn't actually need a medium to travel through. However, as we saw, when light actually goes through different media, we see that light actually ends up slowing down. So we ended up with a section on Snell's law. We started taking a look at if I'm coming in at an angle, I have some angle of incidence as I approach a boundary. Depending on which side of my marching band actually hits the boundary first, I'm either going to bend towards the normal when I go to a medium that's a higher density, or I'm going to bend away from the normal. All that was looking at more so sort of speed of light, light carrying energy. We then took a look at sort of mirrors and lenses in some ray diagrams, seeing which ones ended up converging things, ending up diverging things. Wherever those rays actually intersected, they ended up producing real images. We'll get into a little bit of summary of it in a couple lessons. Today we're just going to switch gears here. Last little bit in this waves optics chapter, I just want to give you a quick taste on relativity. Some of you have come into physics because I hear relativity is weird, I hear time slows down, things like that. I just want to show you just a simple explanation on why we get some of the conclusions of relativity. If you're interested in studying more, you can definitely look in more detail, but at least I wanted you to at least see this equation. This one here, Einstein actually discovered this in the early 1900s. We're going to do one form of relativity called special relativity. Einstein, maybe 20 years after he did his paper on special relativity, he did a notion called general relativity. It was even more broad than special relativity, but we're just going to take a look at special relativity. As we work through this first example, I just want to show you in special relativity, things get weird when you start traveling close to the speed of light. And it's not something that scientists have just made up. It's something that definitely comes out of the math. Although we may not in our lifetime actually be able to run experiments like this, we may not be able to travel around ourselves anywhere close to the speed of light, but this is just some inherent oddity that's inside our universe. So I'm going to start off with this derivation with time dilation, just to show you how times may be different between observers, and then we're going to just look at a few other formulas that special relativity gives us. Just before we get to this time dilation here, I just want to give you an example. What do we mean that things are relative? So let's start off here. Let's say you're just standing here. So you are person A, and let's say you're looking at a friend. Your friend is person B, right? So right now here, both of you are standing, right? If I ask person A, what's person B doing? Person A would say, well, B is at rest, not moving. If I ask person B, what's person A doing? They're at rest, no problem. They both agree, no worries. Now let's say B gets on a train, and this train here starts moving to the right. Let's make up a number. Let's say the train starts moving at 10 meters per second. Let's write down in words here for person A. According to person A, what is person B doing now? Well, person A, at first B was directly in front of me, but because B is now traveling to the right 10 meters per second, according to person A, person B is moving 10 meters per second, just use our convention here, east, positive, all right? Now, what if you were person B? If you were the person on the train, so according to person B, if you were the person on the train, it feels like you're just standing on the train, and you're watching the whole world kind of go by in the opposite direction. So sure, when I first got on the plane, person A was just standing directly across from me. As this train pushes along, however, when I'm over here, it's almost like I didn't move, but A actually went to the left. So we're actually going to say, according to person B isn't moving. I'm standing on the train. I'm totally stationary. But in this case here, according to them, person A is actually moving the same 10 meters per second, but we're going to actually say 10 meters per second left or 10 meters per second west. So the general question I want to ask you here is, who's right? Is it one guy's going east or is one guy going west? Well, in this sort of simplification here, they're both correct, right? According to person B, because he thinks he's stationary, he's actually on a moving, what's called a reference frame. So from his point of view, reference frame, from his point of view, he didn't know that the train itself was actually moving. So he thought he was stationary, just like when you sit in a car, you think like you're not moving, but it's like the whole world is actually passing by you. According to his reference frame, person A is actually doing the opposite. In fact, sort of the conclusion out of here is, yes, they're both right. This actually gives rise to our first relativity principle. So we can write this down here. First relativity principle, even as we get into some weird stuff with dilation later on here, but for relativity principle, the notion here is your physical laws. So all the physics that we've learned, physical laws are the same in any inertial reference frame. Your physical laws are the same in any inertial reference frame. So all the physics, all the F net equals ma, all of those things that we've been learning is the same. It doesn't matter what reference frame you look at. It doesn't matter whether you're talking about person A or person B. This reference frame here in general does talk about sort of like a point of view. Am I asking person A or am I asking person B? And I introduce another term here, this whole notion of this word here, inertial. The word inertial comes from the word inertia. Inertia is a property that matter has, that it's sort of a resistance to acceleration. If I'm in an inertial reference frame, basically it's a frame that there's no acceleration. In fact, all of special relativity is based off an inertial reference frame. Sure, we could have, in this case here, we might call him a ground observer, right? I'm standing on the ground. Or I may have you can call him a train observer, but more generically, you can say a moving observer because he's actually moving. In both cases, even though there is relative motion between the ground and the person, it's all no acceleration. It's all constant velocity. So that's what the relativity principle says, right? It doesn't matter. Nobody's right. Okay, they're both right, right? So that's one of the relativity principles here. What's really weird, as we'll see in this time dilation formula, however, is although there's no, sometimes you can say here, there's no preferred, can't spell here. There's no preferred reference frame. So it just depends. If you want to talk to person A, he's going to say something. Person B would say the opposite, but there's no preference. There's no, A is more right than B. Okay, that's the idea there, right? Intuitively here, you sort of disagree with me there. Well, when I say who's right, we're sort of leaning towards, well, isn't A more right? Because A really isn't moving, and B actually is moving, and he's just silly, and he just doesn't know that he's moving, right? Well, just to sway your bets a little bit here, you're right. Person A sort of looks like he's on the ground. Person A is, yes, he's definitely not moving. But what am I standing on? Well, I'm standing on the Earth's surface. Is the Earth just constantly just sitting there? Well, no. In a day, the Earth actually rotates around. So in fact, when I'm saying I'm standing on the Earth, I'm also in motion, and I'm not aware of that gradual sort of twisting around in the Earth motion. Then you might say, okay, well then, if the Earth has this problem, it's rotating around, I need to be in space. I need to be floating here. That way I can tell person A, oh, you're actually twisting around with the Earth's surface. That way, I have the best perspective. But even in that case, I may not be correct as well, because this planet here is actually also revolving around the sun. So even if I just capture the rotational motion, you can see that this conversation just gets endless here. But the key feature here is, again, we're not talking accelerating reference frames, right? The frames are just going to be going at constant velocity. In some sense, it's unclear who's a ground observer, who's a moving observer, but regardless, this first relativity principle says is there is no preference. There is no one person has the better view, has the more correct answer. In fact, everyone is correct relative to their point of view. What's really strange here as we get into this next derivation here is, even though there is no preferred reference frame, this second feature here is, we can call this a constancy principle. There is something that is constant in all of this relativity, right? If person A would say this, person B would say this. Even things that are fundamental that we say, well, mass doesn't change, conserved, right? Time doesn't change. Like we agree, these are happening at the same time or at different times or whatever. Turns out in this relativity section, we had to actually throw those by the wayside. Even time is going to start slowing down for moving people and then not slow down for people that aren't in motion. It's weird. But what is constant in our world, again, this comes out of the math here, and this actually is the basis of special relativity, the basis of relativity versus an inertial reference frame here. The thing that actually is constant is actually the speed of light. Speed of light is constant in all reference frames. So that speed of light here, I've listed c, right? C, again, it's in vacuum. And that speed was rounded to 3.0 times 10 to the 8. We're going to use that number quite a lot in this section. So 3 times 10 to the 8, realistically, is actually like 2.9987, something like that, okay? But just two sig figs here, 3 times 10 to the 8. This is actually a little bit weird. Let's go back to our train analogy, and then we'll do this time dilation case here. Let's say we were back to person A. Person A was just on the ground. Let's imagine that there's some light source, so maybe a laser beam here, and we just turn on the laser beam here. This light source here is traveling at the speed of light. All right, no problem. So that light source here is going at 3 times 10 to the 8. If I now put person B in the picture, right, so that's person A, he's on the ground. Person B in the picture, remember, he was moving on the train itself. He himself was also moving 10 meters per second. Now, I know it's not by much, right? If I'm comparing a number like 300 million versus 10, it's not by much. And yet, just like our earlier example, well, wait a second. If person B here steadily over time, if he also starts moving sort of along with the speed of light, he should actually say, person B, let me write this down in words for you here. This is not true, but person B should say the speed of light, how fast is that laser beam sort of whipping by him, is RC, 3 times 10 to the 8, but minus my relative velocity. Right? Because I'm already traveling 10, I'm sort of taking away the 10. You can see that really well here. What if person A was also walking 10 meters per second? If they were both walking 10 meters per second, they're going to be in lockstep, right? The train moves over, the guy also moves over a little bit, right? So because he's actually already moving 10, we want to subtract that 10 because that's going to keep me in lockstep here. I'm going to subtract that 10 from 3 times 10 to the 8. Speed of light here should be less, and yet what this constancy principle says is, nope. Even though person B is also going at 10 meters per second, person B will also say it's going at 3 times 10 to the 8. And it's regardless of how fast he's going. Huh? How can that be true, right? If I'm standing on the ground, it's traveling at the speed. But if I'm also sort of moving along with it, let's say I even move faster. Let's say I move 50% speed of light, 60% speed of light. Shouldn't I be sort of moving along with the light source? And shouldn't the overall light speed be actually decreased? Here's this notion where time actually slows down on you to make sure that light actually stays the same. So we'll come back to that formula in a little bit here. I'm just going to start introducing to you. This is not just funny stuff that comes out of the math, even though this is kind of curious. But I'm just going to show you how we derive the time dilation formula. How do we see that time slows down to sort of keep this picture consistent again? So there's a nice little comic strip here. Again, we have a person A and person B. Person A is going to be called the space observer because he or she happens to be on a rocket ship. And let's say for argument's sake here, this rocket ship here is made out of something fully solid. There's no windows or anything. He has no clue that he's actually on a spaceship. So person A is just going to be, the experiment is quite simple. There's a lamp at the bottom. He's going to measure the length of his spaceship. We're going to call that y because that's the vertical. And he's just going to measure here, well, if I want my light source, when I turn on the light source, I want the light source to go all the way up and all the way back down. I want to figure out what's the time it takes, according to me, to travel this distance of y. So how you can do that here, pretty simple. We're going to say, actually, I'll write some of the letters for you, summarize for you later on. What we're going to compare person A and person B here. Person B is the person that's on the Earth. Now, again, ignoring sort of the rotation of the Earth here, we really believe that I'm just standing here. Person B is actually looking at this person here in the spaceship. The experiment was still the same. The experiment was turn on the light source. The light's supposed to go to the other side, maybe hit a mirror of some sort, and then bounce back the way it came. Little does person A know is person B sees, well, because the spaceship itself actually has some velocity, by the time the light actually hits the top, the light has actually traveled sort of this trajectory. It hasn't, according to person A, it was just straight up, straight down. In this case here, because the whole spaceship has been moving, it's like the light has physically taken this pathway, and better yet here, as the spaceship moves along again, after it reflects off the mirror, it ends up traveling down this pathway here. So you see, inherently here, they already start disagreeing. However, again, according to relativity principle, both people are correct. Let's just see how this math works out here. So we're going to do this in a section here called time dilation. Right. The word dilation just means it's slowing down or spreading out. So we're going to make a note here. I'm going to prove it to you that the Earth observer, this was person B in our comic, Earth observer and the space observer, the person that's currently on the spaceship A, believe it takes different times for the light to travel. So the experiment was the same. Light was supposed to go from, you know how you at the bottom there's light bulb, light was supposed to go from this side, it's supposed to go up and come downwards. What I'm going to do is I'm going to label some of these terms for you here. Let's start off with the sort of the moving case here. So we have spaceship here, spaceship here, spaceship here. So according to the person on the ground, the spaceship is going to overall in this time, it's going to travel at distance x. The spaceship was traveling at a speed v, and I'm going to multiply it by t. Let me just label these terms for you. This is the horizontal distance that your spaceship goes. Your velocity is going to be the speed of the spaceship. And notice that it's only the person on the ground that can actually see this speed of the spaceship, because the person inside the spaceship has no idea they're even moving, right? There's no windows or anything. They can't see that the whole world is actually going past them. This t is super important. This t is going to be the time according to the ground observer. Right? So the person that's on the ground notices that, oh, your spaceship is flying at this speed here. I'm standing here on the ground, and I'm figuring out, based on my clock, so I have a clock here, based on my clock, what's the time ticking away here that it shows on my watch? So that's going to be t. Let's contrast this, okay? Let's contrast this with the person in the spaceship. The person in the spaceship, again, has no idea that he's actually moving along. The person in the spaceship just believes, well, my light source was down here. Instead of actually traveling through the diagonal that person A can see, person B can see, the person here thinks it just goes a straight up and a straight down. So all we're going to do here is we're going to say, well, what's the length of my spaceship? Let's call it y. Because the light here has to go straight up and straight down, I'm going to travel like sort of double the distance. So what I'm going to do is I'm going to figure out, well, how fast does light go? Light goes at the speed of light c. But this time I'm going to actually multiply it by a t naught instead. So this is light speed, right? It's the light I'm using, so light speed. T naught is actually the time according to the space observer, right? And so far you believe right now they're the same, right? Everyone agrees the time should be constant. I'm going to show you a quick derivation that these t's here are actually not the same. Now y is the sort of the width of the spaceship. What I want is I want it to travel y and then travel back, so it needs to actually double the time. So better yet here, I'm just going to say the width of the spaceship is c times t naught, the time that I believe if I'm on the spaceship, but divided by 2. Right? So I would have traveled 2y, but this is the time just to travel 1y. All right, so I think I have most of the terms I need there. What about I think they call this person A, this is person B. What about person B? For person B, when the light was switched on, light actually travels more so in a diagonal and then travels back down in a diagonal. In a similar fashion, according to person B, this diagonal pathway, I'm going to be traveling the width of the spaceship, right, y again. I'm going to be traveling at the speed of light c, but this is going to be according to my watch, not according to the watch on the spaceship. So this likewise is going to be c times 2 divided by c times t divided by 2. Right? So just to start showing you, we're still believing that these times here should be the same, but I've made a difference in t's here. If the t does not have the naught symbol, it's the time that's according to this person B, it's the person that's on the ground. If this t here has this t naught symbol, usually we call that a rest time. This is at rest, but it's at rest sort of with the phenomenon. It's at rest because person A didn't know he was actually on a spaceship, but he's going to be the clock according to the space observer. So just picture for the time being, they both have clocks, and we just want to see what happens to this. What I'm going to do is I'm going to just zoom in, just look at this side of the picture. So just the triangle picture here. So according to that first leg here, the distance, y, that I travel, according to the ground observer, it's supposed to be ct divided by 2. Right? According to my watch, the light's supposed to go all the way up, and I'm halving the distance because I'm cutting off the other time. This distance here, according to the space observer, is this c t naught over 2. So this is our y, this is c t naught over 2. If I'm the space observer, I'm just watching the light just go straight up, just go straight down. Right? That's all there is to it. For the x, again, this has to be the ground observer because the space observer didn't know that it was actually moving. For the x, the overall spaceship would have been traveling at a speed v. Now, it may not necessarily be c, so it may be traveling half the speed of light or 100 kilometers per hour, or it could be any number. But it's going to travel this whole distance in a total time t, according to my watch here. If it just travels to the top, I'm going to travel this, let's say this is vt over 2. Right? So I'm just sort of labeling these axes for you here. This is just one way for us to derive this time dilation formula. So let's just switch to these triangles here. I'm just going to come along and multiply everything by 2. I don't like the fact that everything is doubled. So what I'm going to have is I'm going to have c times t is going to be related to v times t, my actual speed, and it's going to be related to the person on the spaceship's time, c times t naught. Right? Because we've created a right triangle, we've used it a lot in this course here, we can just use Pythagoras. A squared plus b squared equals c squared. Right? So let's just punch our way through here. V times t, all squared, plus c times t naught. No, you don't need to derive this ever again. Okay, we're just showing you it's not just something I made up. Okay, so I have these ones here being squared. What I'm going to do is I'm going to try to find a relationship. I'm going to try to isolate for t naught. So whatever's not t naught, I'm just going to push it over to the other side. Let me do one middle step here. V squared t squared plus, if I square a product, they both get squared. So this one here becomes c squared t squared. And I'm just going to kick over the v squared t squared term. So this is now c squared t naught squared is equal to c squared t squared, and I minus off v squared t squared. Right? Lots of letters here. And here's our final step here. Well, I wanted to isolate for t naught. I'm going to divide by c squared. So let's divide both sides by c squared. So on this side here, I'm left with just t naught squared. Now what I'm getting on the right-hand side is I'm getting c squared, divided by c squared. So just write this out better here, c squared. So I'm left with t squared minus, this term here is going to become very common, v squared over c squared. It's this ratio between my speed and the speed of light times it by t squared here. Right? So far, so good, right? And then we're just going to take this, I'm going to factor it out, and then I can take a square root. So t naught squared, because they both have a t squared term, the time according to the space observer, I'm going to get a 1 minus v squared over c squared. And the reason why I want to factor it is because then I can square root it. Here's our time dilation formula. This t naught, I'm going to remind you again, the t naught this time is according to the space observer. You can double check we can call that a space time. So t naught is this time here as according to the space observer we wrote earlier. So he's at rest in relation to the phenomenon. This t naught is actually going to be given by, if I square root of t, it's just going to be t. And then I'm going to have this term pop up here, 1 minus v squared over c squared. So where we were always banking on the fact times are always the same. There's no preference in terms of reference frame here. T should always be the same, whether I'm on the space or whether I'm on the Earth. So this is time according to the ground observer, to the person that's physically sitting on the ground. And what's strange here is where I would have expected the math would come out, oh, t naught is actually equal to t. The times are always equal to the same. I've picked up a really weird 1 minus v squared over c squared factor. Right? Now, so that just came out of the math. You just saw us do the derivation. This one here is going to become one of the formulas on your formula sheet here. Just playing around with this math first. So just a thought experiment here. So think for a second about this 1 minus v squared over c squared term, right? Now v here is the actual velocity of the spaceship. whereas c is actually the speed of light. It's the 3 times 10 to the 8. Right? If v is tiny, okay? If the v is small, usually it's going to be small for our everyday speeds. So if we are traveling at 50 kilometers per hour, 20 kilometers per hour, whatever, these are everyday speeds. When I convert those to meter per second, they're only going to be like times 10 to the 1, 10 to the 2 or so. If I square that, sure, it gets a little bit bigger. But when I take something like 10 to the 3, 10 to the 4, when I divide it something like 10 to the 8 squared, 10 to the 16, in this case here, my numerator is way tiny. With the numerator here way tiny, the fraction here is going to get even smaller. As this gets smaller and smaller and gets closer to 0, 1 minus 0 is just going to be about 1. So if v is small, you can make a note here, v squared over c squared is going to be close to 0. You can try it out. We're going to punch in numbers later on. Because this term here is close to 0, this whole term, we're going to relate this to the relativistic factor shortly, this whole term here is about 1. Now that's perfect, right? The t naught is supposed to be t, right? We are supposed to agree that time should be constant. And yet, this is only true at an everyday speed. Now let's think, what if our velocity is actually more than that, okay? So I'll do an example with you very shortly. But if v is big, so if v is close to the speed of light, right? If v is actually close to the speed of light, this v squared, c squared term, they actually fight against each other quite a lot. So let's say v, we usually like things in terms of the speed of light. So for example, let's say, what if v was 0.99 the speed of light, 99% the speed of light? It's sort of neck and neck with the speed of light. Well, let's see what happens to the math here. I'm going to show you that this term here is close to 1. It's not exactly 1. But what's going to happen here is, let's just do the math. If v is 0.99 all squared, 0.99c all squared, and that's all over c squared here. Right? I crunched the math there. When I square a product, the multiply just goes into, so 0.99 squared. This gives me here 0.9801, the blue c squared on top. Oops. C squared on top. And then I divide it by the c squared on the bottom. You notice that that c squared term drops out. This time, because I'm traveling really, really quickly, this time this has some fight against the actual c. The nice thing is if you leave it in terms of c here, you see that the c's just end up dropping out. So if I really did the math in this case here, I would go 1 minus, well, what do I get for v squared over c squared? In this case here, I'm just left with the 0.99 squared, 0.9801. That's actually having a good fight against 1. 1 minus that, this one here, with the square root, is going to actually be close to 0. Not exactly 0. I don't want it to hit 0. It's actually impossible to get to 0. But in this example here, if I took the root, so root of this answer here, let me just write out the whole number here, 0.141, and this one here, just write in words here, this is close to 0. Alright? So, now let's look back at our time dilation formula. When we were at everyday speeds, when the v was tiny, this term kind of died away. 1 minus something that's close to 0 is basically 1, square root of 1 is basically 1, t times 1, yeah, we agree, t is equal to t naught. And yet now, if the space observer was actually, this is the spaceship speed, remember, this is the velocity. If he was actually traveling at 0.99 c, what you can actually do is you can say, well, what time would he say? The t naught is supposed to equal to t. It's going to actually be scaled down 0.141. So let's put some numbers to this here. Let's say the time I believe, this is, remember, according to the ground observer, let's say I believe you travel in the spaceship for 30 years. Where we would have expected the time to be constant, now because I was traveling around such a fast speed, 30 times 0.141 is actually only going to be some 4.2 years. Time has dilated, time is slower, the clock is actually slower for the space observer. All right. So a couple things just to watch out for as you're working through this. This all comes out of the math. This is a real phenomenon. It's not just something that, oh, I just made up. This is the way that science works or whatever. It is, time actually does slow down. We both had clocks where we both thought time should be constant. Time should be the same for both of us. It doesn't matter which frame of reference we are. In fact, as I move quicker, the slower time actually gets. Now here's just a couple cautions as I just leave you with two formulas here. The one formula here is the fact this square root 1 minus v squared over c squared term pops up really, really often. So sometimes what they do is they actually come up with something called a relativistic factor. Maybe I'll just put it over here. So they call it a relativistic factor. Again, we saw that the relativistic factor was only really significant when the v was big, when the v was actually close to the speed of light. Relativistic factor here, sometimes they're going to use gamma for it. It can be capital, it can be lowercase, doesn't really matter. But what they do for the relativistic factor is they actually go 1 over this 1 minus v squared over c squared. So we do have that root 1 minus v squared over c squared, but you notice it's actually a reciprocal. So based on my derivation and based on the way they're formulating here, t naught is equal to t and then this root here. If I actually want to have this one, I'm actually going to go, the formula I derived, t naught is actually going to be t divided by gamma, right? Because if this one here is in the denominator, 1 over this fraction here would flip it back upwards and it's allow me to have it back. So that's one thing to be careful of. Sometimes if they define relativistic factor, they define it here as a reciprocal by itself, so our formula actually ends up being flipped around. Annoyingly, sometimes they also confuse here, well, who's actually at rest here? In some sense, you can say it's actually better to say that the space guy is at rest because the space guy is actually on the spaceship. He's in a locked away spaceship. He doesn't have any windows. He can't see outside. So it's actually best to say he's at rest. And yet, in some sense, the ground observer is also at rest, right? I believe he's just standing on the Earth's surface. I'm not noticing the Earth's rotation or whatever. He is at rest as well. So sometimes when you actually compare it with other notes, things like that, sometimes they actually might switch the t naught and t on you. So just be careful who's the space-time and who's the actual time according to the ground observer. So just watch out for that there. I actually noticed on my formula sheet, I guess I was comparing two different sources. I actually mixed up the next two formulas here, and we'll play around with these formulas in the next lesson here. But we had, so t naught according to t over gamma here. I also, as the time increases, so time dilates, time slows down for the moving observer. We're going to see, based on this consequence, based on other phenomena like this, where fundamentally numbers that shouldn't have changed, we're actually going to see that the mass actually increases. So for that to be true here, the m naught should actually be m times gamma. So if I actually wrote that up for you, gamma by itself was actually the reciprocal. If you can change your formula sheet here, if you can actually get it to read here, m 1 over 1 minus v squared over c squared. I think I had it divided accidentally. So change this one here on your formula sheet. So another consequence here is mass actually increases as you get close to the speed of light. According to who the observer is, it's like the mass of the spaceship is actually going to be larger and larger. That actually helps us explain something else in special relativity. As we get closer and closer to the speed of light, my mass increases so much so that it gets so hard. You need so much force to actually accelerate it that the speed of light actually becomes not only a constant, it's a number that's always true, but it's also some limit in terms of our speed. Basically, our masses are going to get infinitely massive that it's impossible to then accelerate it even some more, and that speed of light 3 times 10 to the 8, even though it's rounded, represents a maximum speed in our universe. I'm just going to leave you with the last formula here, and then we'll practice in the next lesson here. There's also one other consequence. L naught is also equal to, this is also something that I mixed up on the formula sheet, so make sure you correct that for yourself. And this one here looks a lot like your time dilation formula. I'm not going to derive the math for this one here. It follows fairly similarly. In this case here, the length contracts. So the way I do this part here, I know this is weird. I just keep these features in mind. I know that when I go fast, I know time slows, I know mass increases, and I know the length actually gets shorter. This is the length that's actually sort of relative to me. So in this case here, for the space observer is going to the right. The length of the spaceship would be this x. That's the length I'm talking about, not the length of the perpendicular direction. But I just keep in mind just the direction for me here. Time slows, mass increases, length contracts. Do whatever you can to the formula. I don't care who you label to be naught and who's the space-time, rest time, whatever, but make sure that this is true. Time dilates, mass gets bigger, and the length actually shrinks on you. So in the next lesson, we'll flesh this out a little bit more. We'll play around with some of that math, and then we'll go from there. Thanks, guys.